the whole idea behind the first chapter was just to explain that there is something called a thermodynamic cycle, whether it's for power or whether it's for refrigeration. Okay, refrigeration slash heating, they are the same thing. So, and that cycle performance is characterized by something called efficiency, which is work net over Q added, what you get divided by what you pay. And that will remain the same thing here when we go about, today we're going to talk about refrigeration slash heating cycles. So the purpose behind those cycles is to improve, or actually to move heat rather than generate power. So the power cycle job is you give them heat, you get mechanical work. The vapor, the refrigeration and heat pump cycle are the opposite. You give them work and you expect them to do heat transfer. And you would say, well, why that require a cycle? I mean, I can just burn fuel and generate heat and make heat transfer. So that would be the, and you can do this by burning fuel. Here's my fuel candle or something, and that will generate heat. And so here you are happy receiving that Q dot radiation. Okay, so that's very simple, right? But this happened because this T flame is higher than this. So the heat will go from hot to cold all the time easily, huh? I mean, we can just, in the TS diagram, anytime you have TH and T low, the heat will come from here and drop to here. Like think about a hot piece of iron. If we put it over here, it will heat us. The heat will radiate from it, right? Anytime you hold a cube of ice, your hand that's hot will melt the heat, the piece of ice. How? Because the temperature of your hand is higher than the temperature of the ice, and the heat will go this way. So that does not require heating or refrigeration cycle, right? That's piece of cake. What is hard to do is to move the heat from the low to the high. 70-degree house or a classroom, and you want to move the heat to 100-degree ambient outside. And why you do this? Because, I mean, those people in the classroom, they generate Q dot. Every one of us are metabolism basically is generating heat. And if we don't remove this Q dot, our 70-degree will become 72, 73, 75. So we have to continuously move the heat, right? And we need to do it from T low to T high. So when I was undergrad, and in the first time they explained that to me, I thought that was genius. I thought that the vapor compression cycle, you know, is whoever came up with it is really a very smart person. And we, by association as engineer, we should be respected in society. Like every time we move or go to any place, they would point to us and say, wow, those are the people that can take the heat from low to high. Okay, so how does this work? How can you can move the heat from here to here, from the low to the hot? So we need to understand that we cannot violate the physics. And the physics says, ouch, the physics says you have to move from the high to the low, right? So the only way that heat in the classroom can be removed is by having something colder than it, right? So if this is at 70, we actually, the only thing that will suck the heat from our classroom is something coming here at say 60 degrees Fahrenheit or 50 degrees Fahrenheit. Then the heat will fall to the thing, right? And the only way we can transfer heat to 100-degree ambient is if we have something say at 120 degrees. Then the heat will drop from this guy to this guy. So the only question is how we can take that Q and let's call it Q dot low. Why low? Because we are sucking it at low temperature. We're sucking it from 70-degree ambient room or a fridge, whatever the place where we are sucking the heat from. How we can take that Q dot L and make it Q dot H. The Q dot H that we are dumping from high temperature to the ambient, right? Basically, how to go from here to here. So what is the way to go from this point? Let me call it point 1. And we should go to a point 2. What will take me from here to there? We saw in the power cycle, for example, the Rankine cycle, how did we go from the high to the low pressure? What was that? What was that device? Turbine. A turbine expanded you from high pressure and temperature to low pressure and temperature. And as a result, you got work out of it. So what if we work in reverse? That's called a compressor. If you have a compressor, if you have a compressor, and so usually they come with a big area and they go from the small area. That compressor take work. That compressor will take you from the low pressure and temperature to the high pressure and temperature. So we can go there from here to here, okay, using a compressor. Isentropic compressor will look like this, right? You go up like this. That will do it. And if it's not isentropic compressor, because there is friction and there is losses and there is a bunch of stuff, then he will go to the right or to the left. Right, because the entropy need to increase. So let's call this TS and this is called real T. Okay, and that compressor will have an efficiency, right? So if I just, this is not, I mean the screen is good. So it will have eta compressor that will be the small guy over the big guy. What is the small part? The actual work or the real work for a compressor? The smallest will be the ideal work. So W dot ideal over W dot actual. Right? That's the isentropic efficiency of the compressor. Or simply H2S minus H1 over H2 minus H1. What is written here? W dot actual. So go from 1 to 2. Okay. So by doing a compressor like this, you can go up, right? And so once you are that high, you can dump your QH. And then how we can go from the high to the low, that's easy. You can have a turbine that will take you down, right? Or now if I plot the actual pH on a pH diagram, so there's two ways to plot this, all right? We can plot on TS or we can plot on pH. And in today's quiz, at the end of the class, I'm going to ask you to plot the cycle on a pH diagram. So that's the solution. Okay. So remember the TS, how it look like usually? It look like this, right? That's the TS. The x-axis is the entropy and the y-axis is the temperature. On the pH diagram, the P is pressure, is the y-axis, and the enthalpy is the x-axis. So here a compressor, isentropic compressor will look like this, 1 to 2, constant what? S, right? Isentropic compression, you go up like this. On a pH diagram, it would look like this. That's S equal constant. That's 1, that's 2. Okay? And the heating and the cooling part, that happen at high temperature and low temperature, they happen at constant pressure. So you actually have also constant like pH and B low. High pressure for the condenser, low pressure for the evaporator. This is called evaporator. And this is called condenser. And so once you are that hot, you are even hotter than T ambient. T ambient would be like here. That's the 100 degree. Then you get cooled by the air all the way until you become liquid. That's why they call it condenser. So that hot vapor leaving the compressor get cooled, become saturated vapor, and then get cooled until it becomes saturated liquid. And the guy at the bottom, that's the one that go to the fridge. That's the one that go to the classroom. That's the one that's even colder than your low temperature. So it's, let's say this is 70 degrees Fahrenheit. You are lower than it. And as a result, you get, when you come here in that place, you are colder than that place. You are at 60, 50, 40. And you suck heat from them. And what happens? You evaporate until you become all the way saturated vapor. And you can even get a little bit superheated. Why you want to get a little bit superheated? Because the compressor that you're gonna feed work better if you don't have liquid. As a matter of fact, practically they put some kind of a dryer that you don't want liquid to go to the compressor, right? And the compressor go 1 to 2, and then all the way in the condenser become saturated liquid, and then you go down like this with a throttling device. So that throttling device could be just like a small capillary tube or a throttling valve, something that do what? Take you from this P3 all the way to B4. So as the pressure drop like a rock like this, the temperature also drop like a rock. Okay, and you are ready to go into the evaporator. Okay, so what is genius about this, at least that's what I thought it was genius when I was undergrad, is that you are still doing the natural way of moving heat. You're always moving from hot to cold, but you still manage at the end of the day, by this cycle, you end up managing to take temperature or like heat from low temperature and dump it at the high temperature. So this condenser will be outside your house or outside your fridge, sitting here and going from 2 to 4. That's basically an outside ambient at 100 degrees Fahrenheit. And then there is a wall like this, that's your house. And the evaporator will be sitting over here, getting, sorry, what did I say? 2 and 3, 2 and 3. And so he's getting 4 and leaving at 1 while sucking Q dot L. Okay. And this is dumping Q dot H. So let's not call this T ambient. Let's call this T hot. And this is TL. Okay. And in between them, there is the compressor, right? And there is the throttling device. Does this cycle make sense? So now we are not going to say efficiency of this cycle, okay? Like the power plant efficiency. No, we're going to have something else to characterize it. We call it COP, coefficient of performance. And despite the change in the name, it's still like the efficiency. What we would like to get divided by what we are paying. So obviously, what are we paying in this problem? W dot compressor. That's what we are paying. In kilowatts, in horsepower, whatever the unit you want. And what are we getting? Q. Which one? Q dot L if this was a fridge. if you care about is the TL, I want to get that place really, really cold, then it's Q dot L. Okay? But if I wanted, if this was a heat pump, meaning this is winter, and we actually want the 100-degree is not the ambient. The 100-degree is our house or our water heater or whatever the heating place we want to heat. And at 70-degree is not our room. No, the 70-degree is the ambient. So you're going to take heat from 70-degree ambient and you want to heat the water tank to 100-degree so that you can take your shower. So in that scenario, what do you care about? The Q dot H or Q dot L? Q dot H, that is your goal. So there is COP that is called Q dot H over work done compressor. So when you do this, that's called a heat pump. And when you do this, Q dot L, that is a refrigerator. Okay? So at the same cycle, that can work as a refrigerator can also work as a heat pump. As a matter of fact, our air conditioning at home is like this. And we will see in the cycle, it's done just by flipping the flow coming from the condenser, coming from the compressor. So if we are winter and we want the hot place to be inside, the exit of the compressor, 1, 2, 3, 4. That exit of the compressor need to go to our house. The exit need to go to our house. That becomes a heat pump. But if it was summer and we want our house to be cold, then the exit of the throttling valve 4 should go to our house. So whether we send 2 to our inside unit or 4 to the inside unit, that is the difference between, are we want to be in the winter mood or summer mood? You want to heat the inside or do you want to cool the inside? Okay. So very smartly, they have the compressor and the throttling device with a 3-way valve so that you can switch the exit of the compressor and say, go outside, it's summer, or go inside, it's winter. Okay, and of course, the throttling valve will do the same. They actually have 2 throttling valves ready to be engaged, right? So that is a power cycle, and our job is basically to calculate this and to try to make it even better, higher and higher. So why didn't we call this efficiency? I mean, it looked like output over input. Why we couldn't just call it efficiency? So let me make a cartoon of the cycle one more time. So by the way, did you see how on a BH diagram, you see how 3 and 4 are vertical? What does that mean? On BH diagram, if 3 and 4, the flow in the throttling device show up as a vertical line on a BH diagram, what does it mean? Not isentropic. I mean, you think it's isentropic because you think, see, this is isentropic. This is constant S here. Which is constant H, right? So it's constant H, right? It's constant H. Why? Because if you apply the first law to that throttling device, Q minus W equal to M dot delta H. How much work in the throttling device? And how much heat transfer? 0, because it happens so quickly. So it's really just constant H. So whatever H at 3, it's exactly the H at 4. Okay, on a TS diagram, let's make it nicer. On a TS diagram, this cycle, here is the compressor. The compressor will look up like this, 1 to 2, and then the constant pressure heat rejection at the condenser will take you like this, constant pressure heat rejection, all the way to this. That is 3. And then 3 to 4 going through that throttling device will look like this. That's called throttling. On a TS diagram, obviously it's not isentropic. The entropy is not constant. Why? Where is the losses? So that's adiabatic and it's a small pipe. Well, tons of friction. And look at the loss of availability. You had this high temperature and pressure and you dropped at very low pressure, right? So no, it's tons of reversibility, huh? But it does the job. It does the job of what? Dropping the temperature. That's what we wanted, so that 4 is now ready to go to the cold side. All right? So as engineers, is anything is uncomfortable for you in this cycle? You see something here and like, man, that is so screwed. Why they are doing this? What part of this you don't like? Having said it's like genius cycle, I love it. What part you are like, that's not right? Anyone? Free quiz. Did you have a free quiz last time? The time before, right? You don't remember? Your name is Eric, right? Robert? Okay. Someone was here at that place and he got a free quiz first. It was you, okay. Okay. So, what is bad about the cycle that make you not happy? Anything? Yes. This is assuming ideal what? Ideal. Yeah, well, ideally it's isentropic, but in real life he will go a little bit to the right. Yes. So this is 2s and this is the real 2. Yes, and so we have in Oklahoma State University, we have really a professor that specialized in the compressors of air conditioning. His name is Craig Bradshaw. He actually is the one that teaching thermal fluid on the other side some years. So I mean, we will do a lot of work to improve those compressors, right? There's a lot of research on compressors because you can see that they are really the heart of all the vapor compression cycles, all the refrigeration cycles. So I mean, if you improve it, okay, anything that not comfortable. How much in the wet region? What do you mean? So if you are saying that this is bad, why we are in the wet, and I wish we were all outside, right? So the outside, there is something called Brayton cycle, and it's all air, and so it's basically something like this, right? And this is the opposite of what is Brayton cycle. Did anyone hear about Brayton cycle in Thermo 1? This is TS diagram, and this is just a turbine, right? Condenser, compressor, combustion chamber, and turbine. So this cycle is a cycle of jet engines, all jet engine, all gas turbines run on Brayton cycle, kind of work net. So you give it Q dot H, and you lose some Q dot L, and you get work from the, of course, the compressor take work, but the work is smaller than work net. This is a very old cycle. You know, they had this on paper forever, but they just couldn't make a compressor that take less work than turbine and run on the same pressure until the Second World War and Germans start having those jet engines, right? So if it run this way, that's a Bauer cycle, we get work. But if it run that way, it's a refrigeration cycle, and it will be like this. And what you get from it, you get QL sucked from and thrown to QH. So you get a refrigeration cycle by reversing the Brayton cycle, right? So this is done. But so, Eric, again, what's your name? Sorry. Robert. Robert saying, this is not nice. I wish it was all outside. Why? Actually, this is really nice. Why it's nice to be in the wet region? Constant temperature, heat addition, and constant temperature, heat rejection. What is the best cycle ever? What did we call this cycle on the TS diagram? Carnot cycle. And just like last time, when we had it like this, and it was giving us power, if you reverse it, I'm reversing it, then it is a refrigeration cycle. And this one doesn't give you work. This one, you give it work, net, and you get Q sucked from the low and sent to the high. And just like the best power cycle is ever was Carnot cycle, right? And last time we said eta thermal for Carnot cycle was how much? Anyone remember? 1 minus TL over TH. Or simply it was TH over TH minus TL. And that was because it was QH, and on top we had work net. So work net was this, which was what? QH minus QL divided by QH. So that's why it was like that. And that's why it was like this, which what we all memorize. That is the thermal efficiency of Carnot cycle working as a Bauer cycle. Okay, so if the Carnot cycle is working as a refrigeration cycle, okay, and see how I'm reversing it, it's going the other way on the TS diagram. If it's a refrigeration cycle, we will also have COP for it. What is the COP of a refrigeration cycle? Q dot L over work net. Yes, work net, which is right now just a compressor because the throttling device doesn't give us anything. And so what is work net? This is important for the quiz today. What's work net? Well, QH minus QL. Why? First law of thermodynamics. I mean, this cycle, I see three things in front of my eye. Work added, Q dot L sucked, Q dot H removed up, right? So work plus QL equal QH, right? And so this is for every cycle in the world, not just Carnot cycle. Any cycle, any refrigeration cycle in the world, the COP is what you get, QL, what do you pay, QH minus QL. Okay, but for Carnot cycle specifically, this is important. For Carnot cycle specifically, this, because of the shape of the cycle, because of that rectangle, this become, what do you think? Give me a guess. What does this translate to? TL over TH minus TL. So this is the efficiency of a Carnot refrigeration cycle. That is the best COP that you can expect. That's your benchmark. If you get closer to this, you did amazing job. If you are far away from this, then there is room to improve. Make sense? Right? And I mean, naturally, COP for a heat pump that's working on Carnot cycle. First of all, COP for any heat pump is QH divided by QH minus QL. See, this time the job, the task, the target is QH. Okay, so that's for any cycle node, but for Carnot specifically, this become TH over TH minus TL. That is the COP of a heat pump running on Carnot cycle, the perfect rectangle. Okay, that's what you are trying to compete with. So back again to the what is wrong with the traditional vapor compression cycle. So Robert said, I don't like that it's wet. I'm telling him, no, that's actually good because it looked like Carnot for me. And also because that latent heat going from this to this, that's a lot of energy, a lot of energy, like going from H, what did we call this? HG to HF. In the thermal table, HG to HF. That's the latent heat. That's like 2000 stuff. Huh? It's a big chunk of, I wish we had the same thing over here, right? But I mean, because this thing takes us to the right, we have, anyway. So constant constant temperature heat rejection and constant temperature heat addition is not really a problem, no. What else is not good? And you remember when we calculated the COP? What's your name? Steve said divide by work compressor, and I said, you mean work net? But then it's work compressor because the throttling device is not doing anything. That's your head. So what you don't like then? What do you don't like? You are saying this part? You are talking about this part, right? Right. You are right. Actually, this part is a problem, right? That's for sure. But I mean, what can you do? You just have to go. I mean, the best. So the best compressor, is it isentropic, or there's actually better compressor than isentropic? I mean, this is the real compressor, right? And even a worse compressor will go more to the right, yes? The worse. Let me switch to that screen. Come on. So again, pH diagram. So this is 2S, but the real one will actually take you all the way up to here, right? And that is said. So the best compressors are isentropic or something else. What do you guys think? Don't like this software. What is the best compressor that we can have? What is the best compression process? The best compression is actually not isentropic. The best compression is isothermal. Okay, so that's why in real compressors, especially for multi-stage, they always try to do what in the middle. They try to have you ever seen a compressor, multi-stage compressor? Like you do the first stage and then there's something you do before you go to the second stage. What do? You cool. You intercool, right? So an intercooler reduce the temperature and try to achieve that dream. What dream? Rather than going, this is on the TS diagram, here is constant, right? And that's the isentropic compression. Surprisingly, the best work, not isentropic, but the best work is actually going isothermal. If you go from this P low to B high, isothermal, you spend less work. But how do you do isothermal compression? What you are supposed to do? Because as we increase the pressure, the temperature increase on us for isentropic. So what they do is they go up to one stage, just take the pressure this much, and then cool again to T ambient. Then go up a little bit, then cool again to T ambient, and then go up. So this is not really isentropic, but this is only 3 stages. Well, maybe you can make 5 stages. Mickey can do 8 stages. So eventually, if you do enough stages, how it will look like on a TS diagram? That line going from 1 to 2 will be something like this. But that requires a lot of intercooling. It requires a lot of heat exchanger area. So that's why it's expensive. You need to buy all those heat exchanger in the middle. So it's the difference between a lot of money upfront building that multi-stage compressor and between just paying along during the run, while you are during the life of this compressor, is always like taking more electricity from you. The electric motor is using more energy. Okay, but isothermal compression is definitely cheaper, and so that's why at one point a company wanted to store air at high pressure as a way to store energy. Imagine all those wind turbines running when we are not using them at night. People are not turning their houses and stuff. And then when we need them, they are not there. So I remember one time we were visiting the Jenks station across the river from the gathering place. And the guy there from BSO, he had they have a bunch of wind turbines they own. Actually, Oklahoma is the 3rd state in the USA in how much wind energy we generate after Texas and Iowa. So we are really doing a lot of wind. But he was like so sad. He was showing us the histogram of the wind turbine, and he said, "Look, see, the wind turbine were all running at 6 o'clock. Before 6 o'clock, 6 o'clock they shut down the wind. The wind shut itself. Candle." So like he was like, when people needed the electricity, the wind was not there for us. And so they need storage. They need to store that energy. And so this one company basically said that we can store the energy in form of compressed air. And then when we need electricity, we just use this compressed air and we run turbine with it, like gas turbine, run just from compressed air. But the problem was when you compress like this. That takes more energy than what it takes. And then when you expand from 3, you'll not go to 4, you go to here. This is 4S and this is 4. So the amount of compression is actually less than the amount of turbine. Second law kill you on the way up and kill you in the way down. So they said, well, the only way to make this work and you get your energy back that you stored, is to go isothermal. So they invented isothermal compression, but in really very practical way. Rather than having a lot of heat exchangers, and that would be expensive too, they did what? How you can make the air get compressed isothermal. I want you to figure this, search for them. And they actually got a patent for it, and they raised millions of dollars from investors, and they built an actual not power plant, but energy storage plant that can store the air isothermal. And then when you want that air, it will come really cheaply. There's not that much energy that end up using in storing. So I guess all those are good ideas for you to think about the Baker Hughes as well. Because I mean, if you can reduce refrigeration cycle energy requirement, that would be a good thing. So the thing that I wanted one of you to say is, this 3 to 4 is bad. Why 3 to 4 is bad? That would be nice. Yeah, you get more QL if you can do this, right? But also, what's bad about it is H3, although H3 is equal H4, I lost. What did I lose? Yeah, I lost availability. I have very high pressure stuff, and I just dump it down free of charge to, yes, I got the low temperature, right? I mean, this was your refrigeration cycle, that was the point. But you know, like it was like so high. And was there is any way I can lower its temperature and still get something? What can take you from high temperature and pressure to low temperature and pressure and give you something? Turbine. So turbine here would be ideal, except what? Why not everyone is using turbine in this cycle? And they are using just a small capillary tube that kill the pressure and take the temperature down with it. And they call it a day and we are happy. What's wrong about having this going to a turbine? It's wet, excellent. It's wet, and it's not then, if you're gonna have something here, it's not gonna be called a turbine, it's gonna call expander. That technology is not there yet. To have an expander that take liquid and expand meaning lower the temperature and pressure and get work, you need special design. It's not gonna be regular turbine with plates. You cannot shoot those plates with water bubble mixture, right? I mean, remember in the Rankine cycle, and we said in the project how you have to do what? You have to determine, or you have to set yourself, I cannot get any wet than this. There is an X here. When I'm coming down in my turbine, I want this turbine to live. Therefore, I'm going to limit myself to X, I don't know, 0.8, 0.9. You guys will figure it out. But we said, you cannot go there. So now how you are telling me, come from here and expand in a turbine? That will be the end of that turbine, right? So, but there are design that is not regular turbine, that still can get some work. But what doesn't make people really work super hard on this area is when you look at this edge and that edge, I mean, you want to get some work out of it, right? Is that there is not really that much difference. You're not going to get that much enthalpy in that area. So that expander is not gonna give you a lot of work, but still you can get work if you can develop something like this. All right. So that is the Weber compression cycle. So now let's look at the lecture notes and see what is the equation in the book. All right. So power cycle, we talked about this and how the efficiency is like that, right? And in chapter 2 part. So this is the part of chapter 2 that's related to refrigeration in heat pump. So in refrigeration, that is what is happening. You're gonna get Q from very cold, adding work, do your magic and take the heat up. Okay. And notice how, again, the first law simply say that work cycle is, or work net is Q minus Q, right? Because in that cartoon, first law say this plus this equal this. Remember that today. So the COP, the COP of the refrigeration cycle, they call it beta. And the COP of a heat pump, they're gonna call it, what do you think? Gamma. So beta is the COP of a refrigeration cycle. It is Q low or Qn divided by work net. Q low over work net. That is the COP of a refrigeration cycle. And that work having to be Q minus Q. And for a heat pump, it's the same cycle, It's just that you care about this place. You care about the heat part. You care about the place where you're dumping the heat. So when it comes to the, of course, the work is always the difference between them, right? But when it comes to the how you quantify the performance, it's gamma. And gamma is Q high or Q out divided by work net. Okay, Q out over Q out minus Q in. Right? And so people could tell you typical question, really gift question if someone asks you about. Calculate the coefficient of performance. And well, it's a heat pump. So a heat pump, then I care about what? QH over work. And in this problem, he said, here is the QH is 900. And he didn't say the work, but he said the Q low is 600. So QH is 900 and Q low is 600. And you need the work for the COP. So how do you get the work? The difference between QH and Q low. Does this make sense? Pretty simple, right? So last week, actually, I was in attending the DOE, Department of Energy, peer review. So those are all the people got funded from the Department of Energy, and they were reviewing what are they working on research on. And every one of those projects is funded by like, $1 million, $750,000 million. And you can see there is a lot of research done, not just this, but in improving the refrigeration cycle. So heat energy saving and cool energy saving compared to all this are compared with the traditional Weber compression cycle. So this is what Robert was telling us today. When he said, I wish it was all air. That is Brayton heat pump. Okay, so the saving is like what? Less than, 0 to 25 is over here, right? So you can see there is actually a lot of research trying to improve the cooling cycle, that because a lot of houses are using this cooling, a lot of energy, like maybe 30% or more or less of the energy that some people say 40 of the energy that we spend in the USA, 40% transportation and 40% more or less heating and cooling. That's where we spend our energy. Okay. The industry is like taking 20% or something, but we spend a lot of energy in cooling and heating in our homes and residential places, and right? So I mean, 1% increase. Imagine how much energy we are using in the USA, right? And the world, of course, right? Yes, there is a second class acceptance. Okay, so now in chapter 10, he go in detail in the site, right? He will start plotting them on the TS diagram and DH diagram, and then you need to be able to calculate all those points, so that rather than in chapter 2, it was all about just here's your QH and here's your QL. But in the next chapter, in chapter 10, when that's the real heat pump cycle, what we need to know is the problem will not start by this QL and QH, but the problem will be if I have this T low and TH, you know, calculate for me what the vapor compression cycle COP would be. So you need to be able to say what is the work compressor to start with, right? So to get the work compressor, what is that? That's going to be m dot H2 minus H1. 1 and 2. So you actually need to calculate H2 and H1. So he will need to tell us, well, how we can calculate H1 and how we can calculate H2. So how do you calculate H1? Just knowing given TL and TH. Required, and it's a refrigeration. So the coefficient of performance is going to be called what? Beta or gamma? Refrigeration, we call it, yes. So you, when you see something like this, your head is going to the price. The main equation that will get that beta is basically what? Work over Q? No, it's Q low over work, right? Which will translate to H1 minus H4, and the guy at the bottom, work compressor, is H2 minus H1. So just like the Rankine cycle, your head is telling you, I need to get all the H's, right? I need H1, H2, H3, H4. Fortunately for you, H3 and H4 are the same, so we'll just get one of them. Also, the ideal cycle will have this as saturated and this as saturated, right? That's the ideal cycle. But in real life, the one will be a little bit to the left or to the right, a little bit wet or a little bit superheated. A little bit superheated to protect your compressor, right? And the same thing for the condenser. The condenser in real life will be a little bit what? Here, what do we call that? When the liquid is on the other side of the saturated line, what did we call it? Subcooled liquid, or there's another name for it. Compressed liquid, remember? It's either compressed or subcooled. It's basically you are saying, comparing to the TS, T saturation and B saturation, you have higher pressure than B saturation. That's why you are called compressed liquid. And you are colder than T saturation. That's why you are called subcooled. Okay? So solution. I need to get H1. How am I going to get H1? It's going to be HG at T low. Right? This T low, he said, this running at, I don't know, 10 degrees Fahrenheit. My fridge is like 4 degrees Fahrenheit. The freezer is 4 degrees. And the fridge is what, 36, right? We said that 36, the fridge recommended, was it 38? Anyway, so let's call it 10 degrees Fahrenheit, and let's call this guy, this TH is say 100 degrees Fahrenheit. By the way, this line this line that I'm plotting here, is that constant H or constant T or constant P? Yeah, that's pH diagram, this constant P. So when I say TH, that's only this part, that's TH. And then this is all cooling, cooling, cooling until it gets here. But this is T low, right? Because it's in the wet. So TL is constant during the wet. You will understand this when you look at the TS diagram of this cycle. It's like this. See that is TH. And then you go like here, and then this. So this is T. But only this point is TH. Okay, so we got ourselves H1. Okay, now I need H2. How am I gonna get H2? I need two property for H2. What are the two properties that I know? I know S2 is gonna be S1. So maybe we should get S1 too. How can I get S1? SF at T low, right? It's saturated liquid. And so then we would say that S2 equal S1 because it's isentropic. Make sense? And we know TH. Very good. So T2 is TH. And so those two guys together, you'll be able to get H2. Okay. And of course, you should also get B2. And that is B high. Make sense? So now, how am I going to get H3? By the way, this is H2S, right? How am I going to get H3? It's going to be HF at B high. Right? Saturated liquid at that pressure. Right? So notice how this is all one pressure. This is pH. Yes. Sorry. Yeah. I am really sorry. Actually, I'm looking here. I'm not seeing here. Thank you. And actually make this bigger too. And maybe we don't need to see this. So I was saying that this is all just one pressure. So whatever pressure you got over here, it's going to be here. Right? So we got ourselves H3, which also happened to be H4. This is how you get all the H's. Except that the only bad thing is that this is only H2S. We didn't really get H2, we got H2S. Right? Which happened to be at the same pressure, so we are fine with B2. It's just that when we do the eta and we would like to say H2, it's H1 minus H4 divided by H2 minus H1. So that's not H2S, it's H2. So what do? You would say, well, H2 is going to be a little bit bigger than H2S. By how much? By eta compressor, right? So you calculate H2S, and then when it comes to H2, it's going to be given by this guy, by eta compressor, isentropic compressor efficiency. Okay, so the solve of this problem is that pH diagram and how you can get the H's on those 4 cycles, just like what we did with the Rankine cycle. right? Very good. Yeah, go ahead.
What was that final bit of the
Right. So the COP is H2 minus H1 divided by H2 minus H1. Why? Because that is work compressor, right? But it's H2. But what we calculated was H2S, right? H2S. So what is the relation between H1, H2 minus H1 and H2S minus H1? It's eta compressor. So let me write eta compressor over here. Eta compressor is small over big. That's why it's less than 100%. What's the small? The small is the ideal work. The actual work is way bigger. So the ideal work is H2S minus H1. The actual work is H2 minus H1. So if you want the H2 minus the H1, it's going to be the H2S minus H1 divided by eta compressor. So it's easy to calculate H2S because you know the entropy, you know the pressure, or you know the entropy and the temperature. You'll be able to calculate H2S, and this will be given. Then you can calculate your H2, which what you really need for your coefficient of performance. Okay. So sketching is really important. I think we need to be able to demonstrate that cycle on a TS diagram or BH diagram, or some years I asked them for both of them, because I also think that looking at that cycle on the PS, the BH diagram, can give you ideas how to improve it. You need to visualize the problem. You need to see where is the weakness in the cycle. And besides, as engineer, I told you before, it has been proven that we understand figures more than the general public. Okay, engineering students understand figures more than other students in the university. Okay, so we need to be able to sketch it, and we need to be able to calculate the H's and then the COP. So compressor, condenser, expansion valve / capillary tube, right? And the evaporator. This is the four guys. And that wet region here and that wet region here, that two phase mean liquid and gas. It's good because it takes a lot of energy to condense and a lot of energy to boil, right? So, and from Carnot cycle point of view, this is nice. You know that you are adding heat while you are maintaining the same temperature. That's way better than doing this. Okay. Why it's too better than this? Because when you're doing something like this, you are heating or you are cooling with something that is lower than the lowest point. So at the beginning, when you were doing this with that guy, there's a lot of big temperature difference. That's not nice from thermodynamics second law. Okay, when you're using very hot to heat something cold, that's not a great idea. That's why a lot of cycles get better by doing something called multi-effect. They divide it into small parts, and every part gets to exchange heat with something closer to it. Okay. So dry compression, What's dry compression? You leave the evaporator saturated or even superheated so that the compressor does not deal with liquids. Okay, and the compressor is adiabatic for sure, isentropic, amazing, isothermal if we can, the dream, right? And in each one of those, the evaporator, condenser, compressor, just like the Rankine cycle, the first law, which has also delta kinetic energy and delta potential energy, what happened to those guys? We neglect them. Why? Because the enthalpy is just too much. So don't ever forget that the first law, don't ever forget, because maybe at one point in your own application, it will not be the case. And you really wanna really harvest that energy, the kinetic and the potential. So in the condenser, when I'm going from hot compressor exit to the exit of the condenser and dumping the Q dot H to the outside or the hot ambient, the first law actually read this, always Q dot minus W dot equal to the unsteady term that I'm not gonna write here because it's gonna be steady state, plus M dot, and then inside this M dot, there is delta enthalpy plus delta kinetic energy plus delta potential energy, right? And so it's nice to start here so that you remind yourself, I'm gonna neglect this and I'm gonna neglect this, okay? And since this is a condenser, I'm gonna neglect this. When it's compressor, I'm gonna neglect the Q, right? And so that make the Q dot equal to M dot delta H for the evaporator and the condenser. And for the throttling device, both Q and W is 0. So that make why the throttling device have delta H equal constant. So that law applied to the throttling device would say delta H is the same. Applied to the compressor, it will be work equal M dot delta H. Applied to the condenser and evaporator, it become Q dot equal M dot delta H. Right? So you can see in the evaporator, Q is M dot delta H, in the condenser, M dot delta H, in the throttling device, H equal H, right? And this is the beta, and the maximum beta, where it's coming from, Carnot. Okay, and for Carnot, it's T low over TH minus T low, or what they call it, T cold and T hot. Questions? So here is going to what happened in the real cycle. What happened in the real cycle is a little bit superheat, right? And when you go up, you don't go to 2S, you go to 2 by the isotropic efficiency of the compressor that we just wrote. And when you cool, you don't finish here, you finish a little bit subcooled, right? And so you go lower than the temperature, the low temperature you're trying to get heat from, and you go up on top of the TH that you would like to remove the heat to. Right? Questions?
Yeah.
Yeah.
You don't have any state.
So what is this TH and TL? That is the environment that you are moving the heat from and moving the heat to. So if the air outside right now in Tulsa, Oklahoma in August is 90 degrees outside, our compressor, and actually you can see it from the second floor kitchen. If you go to the second floor kitchen on this side, it's like I see it all the time when I'm like making my coffee. I always look at the chiller. It's really beautiful. You have to look like how big the condenser unit is. Huge unit with big fan. It's actually, I think it's how big? It's like all the way from here to that wall, to the first bench. That's how big, and it's a square. Really big, with like fans everywhere and big fans to circulate the air to cool it. So that compressor, sorry, that condenser will have to have a refrigerant even hotter than the 90. How hot it is, what is this big delta T between them? We will see this when we do heat transfer next. Not next, but like in a few lectures. So, but the bigger the delta T between this guy, the refrigerant, and the ambient that you are transferring to, the smaller the size. But you have to spend a lot of energy to go that high. So again, it's the compromise between, do I want to build a smaller heat exchanger because I don't have a space? It's a tight unit, but then I pay every single day in electricity. Or do I want to build as big surface as possible? And therefore now I can have very small delta T between them. So my compressor does not have to work as hard. Yes.
Just to clarify, the purpose of calculating the beta value.
Right. You mean the ideal beta too, right? The
ideal use those or use those
that's an excellent question. So if I'm comparing my cycle to an ideal cycle, should I assume the TH is here or should I assume the TH is there? I would say I assume the TH is ambient. The fact that your unit that you made for us is going up even higher, that's on you, on the manufacturer, not on the environment. Carnot wouldn't need the delta T. Carnot would be just on the TH, ideal. So, I mean, it actually transfer heat without any temperature difference, as well as it compress isentropically too. I mean, imagine that, right? Good. So now, why you have to convince your family to not to set the thermostat really low in the summer? Because when they say, Daddy, we want it to be at 70, rather than 75. If they want to go to 70, the refrigerant need to go even lower, right? And that will make the compressor go really a long way, especially that if the temperature is not 80, the temperature is 90. Like in a hot day, you really have to sympathize with the compressor and realize that on this side, he have to go really high. So at least on the other side, don't let him go really low, right? Because that really long distance is a lot of energy. And you can see, you see what happened if I go lower and lower with my TL? What is the bad thing beside the compressor going higher and taking more work? What else will bad happen to us? Beside the work of the compressor, what other bad thing could happen? I can't hear. Raise your voice. If I go low enough, like if that blue line become even here, what happened? No, it's actually, the problem is state 4. State 4, the 4 will go lower and lower and lower and lower and lower. So what happened? What's being eaten right now? Q dot L. Q dot L will have very small amounts. So not only you are killing your compressor, you are also getting smaller Q dot L. And the COP just sucks, right? And this, I want you to think about this, not just as refrigeration, think of it as also heating pump. If the opposite happens, same thing. When that heat pump go lower and lower, because if this was a heat pump, what is the blue? The blue is outside cold, covered with ice or with snow. I remember when we had this like monster snowstorm, was it 2015 or something? We had like huge amount of snow. We dumped it. I kept looking, going outside, looking at the condenser unit that was surrounded by snow. And I know that condenser outside, he is actually, I mean, he's now the evaporator, right? In the winter, this is what's outside. And this is what's inside. So that unit surrounded by snow is trying to do what? Trying to suck heat out of that frozen snow into my house, right? And so, like, there was no way we're gonna sleep at 70. It was gonna be 65 today because, I mean, we just have to keep it above 65 for the pipes, not to freeze, right? But I was like, I kept looking to that poor thing and like, man, how is like he's trying to get heat from that snow, you know? So that's why this is a big deal. And actually, right now, that last week I was looking at the people reviewing in I think, was it some national lab? They are working on a vapor compression cycle that can work with really big temperature difference. How we can improve their efficiency or COP. How we can improve the COP when you have this big difference between low and high. And when will that happen? They are testing it in Alaska, you know, when people are really working on, when they have very cold outside. Of course, our units in our, at least mine in my home, what happened when it realized that the COP sucks like this? There is a small auxiliary unit that uses natural gas, and you can hear that when the temperature gets that cold, you can hear the furnace firing on the attic, and you can see that, you can hear that he's actually saying, I'm not getting stuff from outside. Let me just add heat myself. So now we'll finish by this. We'll take a break after this question. What is the COP of just a furnace? Burning natural gas to heat your unit. The air is going to a furnace where natural gas is there. What would be the best COP you can dream of? What's COP for a heat pump? QH over work. So the COP of a furnace like this would be how much electricity or like how much like fuel is being added and how much QH I'm getting. So what is the best COP that you can expect? 1. But the COP from a heat pump, how much is the COP that you expect from a heat pump? A heat pump that's doing what? Taking heat from the snow outside plus work compressor equal QH. What would be the COP of this cycle? It has to be greater than 1. Why it has to be greater than 1? Because of the Q dot L, because you're adding Q dot L. So you are building all this thing so that you can get this Q dot L. Yes, this Q dot L gets smaller and smaller as you make bigger and bigger range, but still there. So the COP, any heat pump, when you go to Lowe's or Home Depot and you find there's a heat pump, water heater, of course this guy would be better than electric heat pump, electric water heater, right? Because a COP is guaranteed to be more than 1. But electric water heater, maximum COP is 1. He burn, or not burn, he use a heater, heat the water hot, you cannot get more than 1, right? So that's why the heat pump water heater, a water heater that's run on a heat pump is more expensive because they are basically telling you, you will save electricity. So give us some of this saving to us, we the manufacturer that build this thing for you. But it's not just like greedy, no, it's like because the condenser and the evaporator, right? And the compressor is more expensive than just electric heater, which is nothing but a wire, plug it to the power supply, wire get hot, you get the heat. But compressor, bearing, plates, I mean, all this costs, right? Okay, so now let's take a 10 minutes break, restroom break. We'll continue after this. All right, let's start again. So online people, you still hear me well, right? Thank you. All right, so we said that having big difference between TH and T low really caused the compressor to work harder and also caused QL to get lower and lower. Right? So The actual cycle will have those features too, right? He can get a little bit superheated. And why would you get a little bit superheated? Because the TC is here. The temperature in the fridge or the temperature in the room or whatever the cold place you are trying to cool even more is here, and the refrigerant come and he will boil, he will boil until he is all saturated vapor. And if there is still room in the room, he will get hotter and hotter, right? Before the compressor start cooling it down. So there is room to get a little bit superheated because you are lower than the TC, right? You're lower than TC. So there is a room for you after you finish your saturation to get a little bit hotter, right? And we talked about the compressor efficiency. This is the one equation that I wrote for you and it was not that clear. So here it's beautifully written. Eta compressor is small work over big work. What's small? The ideal work. What's big? The actual work. So we use this equation to figure what is H2 if we know H2S. And 2S is easy to get and 2 is hard to get. And notice how 2 and 2S at the same pressure. This is important, especially when you go to a propulsion course and you're trying to look at jet engine. And you're trying to figure out what is isentropic work and what's the actual work. Where does the pressure end up at the end of the compressor? It has the same pressure, but not the same temperature, not the same ensemble. But see how P2 and P2S are the same? So the compressor will just keep pushing you until you go to that condenser pressure. That's the delivery. You need to deliver to that pressure. Otherwise, the flow will not leave the compressor, right? But he can go the short route if it's isentropic and take less work, or he can go the long route because of all the reversibility and take a lot of work to actually go there. Okay. So let's look at it. So the homework, by the way, next week, we don't have class because Labor Day, right? And we don't have homework either, but we have project. The project is due next week, right? And it's due at 8:30, but my recommendation will rate whatever. But my recommendation is that don't wait until Labor Day and do it, do it before and enjoy your Labor Day, right? But I just want you to understand one thing. Why do I assign home like stuff in a holiday? Shouldn't we just enjoy ourselves? And well, in this course, we have 1 meeting per week rather than 3 meetings per week in morning classes. So basically, you're telling me we have Labor Day, we should be off for a whole week. No, we can't, right? So the project is assigned because not of Labor Day, because we are supposed to meet all week long. So we cannot afford not to have assignment on that day. Okay. Same thing, why do we, like in the chat, they were saying, are we gonna go all the way till 8? And one guy said, yes, he keep going until all the way until he does not stop until 8:15. Not because I don't want to stop, but it's because this class is 4-hour credit. And that 1 hour credit, the extra 1 hour, you get 4-hour credit in your transcript, not 3. It's not for free, it's for this 1 hour that we spend and after 7. That's why you get 4 credit and you are 1 hour closer to graduating, right? So let's put it to good use. Let's use this 1 hour to discuss the homework, and you should ask me about the project and make sure that you get all your answer or your question answered. Because sometimes I get the feeling from the question that people ask is that they were not sitting in the lecture, or if they were sitting in the lecture. And I did this myself when I was undergrad. I remember many times when things get complicated, I tell myself, I don't know what he's talking about. I will just figure it out at home. That takes more time at home when you are on yourself by yourself. If you are in the class, you can stop me and tell me, explain this, I don't get it. Right? And I explain more and more. Nothing makes me more happier than you getting it. It's not how much information that I dump on this side. It's really my success as a professor is how much information get received on the other side. So I rather stay the whole lecture explaining what eta compressor is, rather than explaining all the refrigeration cycle in the world just to be really not understood on the other side, right? So use the lecture time efficiently to make sure that you really get it, right? All right, so that's why we have the extra hour after we finish the lecture, because it's 4 credit hour course, and also because I think it will be useful if we work the problem together. So here in this example, the table provides steady state operating data for vapor compression refrigeration using R134A, that's the refrigerant. For refrigeration mass flow rate, that's m dot, 0.08 kilogram per second, find the compressor power. Okay. And in that table, see, actually, this is the hardest part of the problem, to get the H's. If sometime I actually give them the problem like this, especially if the exam is so long, and I know that they don't have the time to go, but it's also mainly there's selfish reason for that, is that I want all your answers to be exactly the same so that it's easier on grading, because when you go to table, sometimes you don't pick the right number, or like you get it approximated. So when you have the table, then everyone doing the right answer will always get exactly the same number, right? But it doesn't mean that we shouldn't be able to get the H's in ourselves. We should, right? So, but if we have all the H's, he wanted work, compressor power. So when we do this, and we say H2 minus H1, that is called what? Specific work. And why? Because it's missing the m dot. And what's the unit of this guy? H minus H would become, unit is joule per kilogram, right? It's the same as the H. But when we do this, capital W with a dot on it, that becomes the compressor power. And the difference is that it has m dot on it, H2 minus H1. And the unit here would be joule per second, because you multiply the kilogram per second times the joule per kilogram, it becomes joule per second. That is the power. In watts or kilowatt, or you divide over 736, you get it in horsepower, right? That is the power. But notice how the COP, let's say COP of the refrigeration cycle, COP P2, huh? That will be same m dot multiplied by the H4, sorry, H1 minus H4. See how the COP does not require m dot, right? Because it cancels from both of them. Just like the thermal efficiency. Didn't really require, for a power plant, didn't require m dot. But when he says specifically, give me the power, you have to put m dot in. Okay. So compressor work, power, sorry, m dot, H minus H, which H? H2 minus H1. I got H2 over here, I got H1 over here. And I multiply by m dot. Okay, here, compressor power. M dot H minus H. Refrigeration capacity in ton. So that ton, you will hear this all the time in the, if you are working with a refrigeration or like HVAC industry, they always, the unit they use is ton. They don't use kilowatt or horsepower, right? Or megawatt. No, they always work in ton. So what is refrigeration capacity? Which one is that? Is it Q dot L or Q dot H? Help, what do you think? Refrigeration capacity? Q dot L, right? That is how much you are pulling from the cold place, Q dot L. So the refrigeration capacity is M dot H1 minus H4, right? And so kilogram per second multiplied by kilojoule per kilogram, okay? And the unit here is, what is it? If I multiply kilogram per second and kilojoule per kilogram, yeah, kilowatt. But then see 1 ton is 211 kilojoule per minute. So that's why you figure out how many kilojoule per minute and you divide over 211, and that will tell you how many tons. But this was not in minute, this was kilojoule per second. So that's why he's turning the second to minute by that 60. So I mean, if it take this much, if it give you this much per second, how much will it give you per minute? Let's imagine 0.08 times 200, let's call this 200. So it's like 16, right? Kind of, let's call it 16. So 16, kilojoule per second. So how much per minute? You multiply by 60 to get more, right? And then you divide over 211. So it's 3 times. So that's how they quantify, you know, like if you're going to figure out does this building have a really big refrigeration capacity or not, you hear the number 75 ton and 40, like big apartment complex or something would have like 70 ton, and if it was a little bit smaller, maybe like 40 ton. The COP of refrigeration, the QL, H1 minus H4 divided by work, H2 minus H1. And you can see he cancel the M dot, it does not matter. Although if he can just divide those two numbers, but in the same unit, not ton over kilowatt, but kilowatt over kilowatt, he will come up with the same number. You wouldn't have to do the, again, the H minus H. So COP of 3, that's pretty good, right? So when I go to Lowe's and I'm looking at the heat pump they have for residential places, they will tell you it has a COP of 8. What is missing here? Should I just like, wow, pretty good, 8, I'm gonna go and get it? Or should I ask about something else? Can someone just tell you your mile per gallon if your car is 40 without telling you is it highway or downtown? You need to know how is this measured. Yes, yes, yes. You cannot just say COP without telling me when it was doing what. Right, right. So they have to quantify the temperature difference that COP would work at. Because as the temperature difference increases, the COP will decrease. So did they get it for COP 0? For example, how is that COP 0? Like over 0 temperature? Because you have to go 5 degrees down and 5 degrees up, so then 10 degrees. That would be the best COP they will have ever in their life. Right? When you are cooling the air in one room, ambient air, and you are heating the ambient air on the other room. So same temperature. Yes, question.
Do you think they would get that number by taking the average difference over that?
Let me rephrase the question. So if I understood right, the question, what's your name?
Charles.
Charles is saying, do you think that COP can be calculated based on the ideal cycle, just like as if it's Carnot, TH minus TL?
I'm clarifying, the product that you look at is one that advertises some standard COP.
Right.
Do you think they got that number from taking the average difference? How they calculate that?
I think they have to specify the temperature, and they do. But if you read the blueprint, you will figure out what is the temperature they tested at. Over here, in just across the river from us, there is Owen, a really big manufacturer of heat pumps. They make custom-made heat pumps, and before COVID, I would take my students every year to check their power plants, and they see their facility, because the guy there, he actually spent millions of dollars building the place where they test the COP of those power plant, of those refrigeration cycle, but in real environments. What do you mean real environments? Well, he actually, the facility is amazing, okay? And there is like, there's one thing more important, not more important, but as important as the COP for all those refrigeration and heat pump units. What is it? What do you think? What do you think is also as important as how much, ton per kilowatt hour I'm paying? More as important as COP. What do you think? Noise. Noise is very important in those applications, right? And so they, in their facility, they have those like acoustically insulated big chambers where they would put the outside units in on the roof of the building, and the inside is inside the chamber. And then over here, what is amazing is that over here, that's the outside. They can simulate rain, snow. They can make ice in those units. So they can really give you the real life environment outside, very hot, very cold. And the same thing for the building, where the people are sitting. They simulate different building requirements, and then they measure the noise. And it's one of the world, basically. There is no at least that's what they advertise. There's no place in the world where you can have this noise measurements, done correctly, because they completely insulated the buildings, right? And they really can put snow and water and rain and everything. Because it's so when they advertise, we are really generating that COP in those conditions. They really they do. So just, I don't know whether we can arrange another visit this year or not, but I think it's really worth it to see their facility. And also, what's really nice is to see the heat units, the heat pumps, and the refrigeration being built. So they don't make the compressor. They buy the compressors, right? You can see when you go to their facility, you can see all the compressors sitting on the shelves for different things, but they build everything else. And they get the heat exchangers, the coil that the refrigerant go in. They also get those. They buy them from all over the world, but they have to have like really big surface area, and then they put the unit together, the unit that has the compressor and two units. We'll talk more about it when we go to the next chapter, the psychometric. But and actually a lot of students from OSU actually work there. I mean, now they are not students anymore, they're engineers, but like when we go there to the visit, you can see people always say hi, because they know me and I know, so they hire a lot, and it's a really very successful place. And they donated a lot of money also to the labs in Stillwater. So they built this called psychometric chamber. So those chambers where you can simulate the outside air so that you can put your unit in it and see how it will function for a very hot or very cold situation. They donate a lot of money so that they can build something like this. Not as big as theirs facility in Tulsa, but they built one in the College of Engineering. And the professor there do experiments. And actually, I think they like one time they said that the football team of OSU went into the chamber one time to simulate, you know, like very hot, like working in the cold condition or hot condition, because they can vary the temperature easily. All right. So COB is function of the delta T. You cannot expect this. Don't expect the COB to function or deliver exactly the same amount at different temperature, right? If the air gets hotter, if your kids went to the thermostat and said, no, we want to be cold, let's go to 60, that will change the COP of the cycle. Right? The isentropic compressor efficiency, right? Of course, he gave you H2S and H2 and H1. So you do what? You do the ideal work over the big one, the actual work, H2S minus H1 over H2 minus H1. Make sense? The BH diagram, that's what's going to be in the quiz today. I'm going to tell you plot the cycle on the BH diagram. That's the sketch I wanna see. Yes.
Explain again the 2S and the 2. I mean, I understand the concept what they are, but like, are you going to be given one? Do you measure the actual? Then you can calculate what the ideal would be. Or...
So those, let's think about. So the question is, what is the compressor efficiency, and which is the unknown here? What should we expect in the questions, in the exam, and in real life too? What is going to happen exactly? So to start with, the isentropic efficiency of a compressor or a turbine, it's always the small guy over the big guy, so that it can be less than 100%, right? So this efficiency has to be less than 100%. So it happened in a compressor that which one is smaller? The ideal work is smaller. The ideal work is smaller. So H2S minus H1 is smaller than H2 minus H1. Okay. So if this guy is like 100 kilojoule per kilogram, you know, this would be 80, for example, kilojoule per kilogram. Just like this problem. And the efficiency would be 80%. And on a BH diagram or a TS diagram, it will look like this. This would be 1 going to 2S, and that line would be constant entropy. But the real line will actually be here, a little bit more to the right. Why to the right? Entropy need to increase if you have not isentropic process. If you have any irreversibility that make you not isentropic, you have to go to the right, right? So I mean, the right on a TS diagram, but doesn't really, it's not on the BH, but it happened to be on the BH diagram, it has to be to the right because it has to take more H to go there. That's why it's also to the right here, because we are expecting more work, right? So this H is bigger than this H. So in the problems, in the exam, what will happen is ether compressor will be given. Okay, so ether compressor will be given, and H2S, you can calculate this easily from any two property. It's a property in the TS diagram or the BH diagram. So if I know the pressure and the entropy, I should be able to calculate H2S. And so you will use this equation then to calculate H2 from it. And why do you want to calculate H2 from it? Because the COP of the cycle require H2, does not require the ideal H, it requires the actual H. It need, when we write the COP, it's going to be something over H2 minus H1, not H2S over H1. the actual, right? So now in design problem, like your project, you can easily calculate the cycle using asymptotic value. Especially that at the beginning of the problem statement, I said assume ideal cycle asymptotic. But then in task 5, someone asked me, can you explain what's task 5 again? What are we doing in task 5? Task 5 is to quantify by numbers how bad / good your assumption are. So for example, you like assume the project was about a vapor compression refrigeration cycle. And you are trying to figure out what is the COP as I go to different temperature, or designing a refrigeration cycle that work between those two temperatures. And you did everything based on isentropic expansion and compression and everything. Then at the end, you would basically say, now let me assume an ETA compressor that is practical, and let me see how does this change my COP, right? So in that case, again, the efficiency will be given, or you will find it from the literature, and you will use it to calculate the actual H2 instead of the H2S. That's not practical. This is the real one. And you will see the difference in the compressor work, and you will see how much does it really change the COP, right? So in task 5, we work as our own devil advocate. We go in our design and basically say, this is horrible calculation. They assumed isentropic, for example, compression. Is that true? That's not true. But then you're trying to find out how far it is from real life. Maybe the isentropic efficiency of compressor is like 95%. And so the loss is not really that big deal. So at 5%, what's 5% between friends? Nothing. So 5%, the assumption was okay. Or is it like 20%? And that's a big deal, right? So I said many times, not many times, almost every single year in the design project, what I always get disappointed from is that they come to this task 5 and they just talk. There is no number, there is no calculation. Because I think it's the last task and they don't have time for it. And they just like, we are done. And so they just say, well, we assume this and assume this, but they never put numbers. You need to basically say, how bad is my number, or how close was it? Right? So that's what you're doing in task 5. And that's what we do with ETA compressor. So it turned the ideal work to actual work. Okay. Let's leave this for the next hour. Yeah, we'll talk about the project in detail. But let me finish this. I mean, we're almost done here too. So you see how 1 go to 2S, those lines are constant S. Okay. And the actual one will go a little bit more to the right. Make sense? Constant S. And look at the constant temperature. So if a compressor go isothermal, you will actually go like this. That's isothermal. So now selecting refrigerants, that is a big deal. So when I was a student, undergrad in the 90s, you know, we were using R11, our tables were all R11 or R22. This is what we were all using in our refrigeration cycle for our calculation. And turned out those guys were horrible for the ozone layer. There was like a big hole in the North Pole or South Pole. There was a big hole that was forming in the ozone layer. The ozone was depleting because of those refrigerants escaping, and they would escape all those refrigeration cycle in every car and every house, you also empty them when you are servicing the cycle too, right? Or there is leakage all the time, and those molecules will come and start reacting and basically getting the molecule will not go away until he kill bunch of ozone. What's ozone? O3, right? And so basically they we have to stop. The world said we have to stop, otherwise everyone will get cancer on this planet, skin cancer, because that ozone layer is killing or basically absorbing what the ultraviolet radiation from the sun. And that's why when astronauts go to space, they wear those shields so that they prevent the ultraviolet radiation from them, right? So they actually kill those things and they start using R34, 134, and that was, so those are C12 and 11 and 22, those are the ones that I grew up with. But then again, the ozone basically killed all those chlorofluoro refrigerants, right? And then they switch it to R30, 134A and 410. Now, what's the problem with those guys? Those are pretty good for the ozone, and we are happy with them. But what is GWP? Global warming potential. So now the problem is they basically add to the global warming. They keep the planet hot. So yes, the ozone is okay, but they are not okay with the heating. So eventually, if the temperature keep getting hot, and they said we have to switch away from those guys, what's the next step? Those are the refrigerant of the future. So what do you think bad about those guys? Read them. Ammonia, propane, methane, butane. What does it remind you of? Barbecue. Those remind me of that I have to barbecue today for my kid. So this is propane and butane and ammonia, and methane. What are all those guys? Those are fuel. Those can combust. So that's why a lot of people now, a lot of researchers are working on the combustion of, like, what if there's a leak? And how we can make the architecture so that those things are safer, so that the houses would not really burn if the refrigerant escape, right? But they will do the job. They will get you. Yes.
Other than
So the question is, besides, even if we keep them safe, if there's any other downsizing, like a bad thing about them, well, they require high pressure too, propane, and they require high pressure, probably will be expensive to handle. And maybe I don't know about their COP, the coefficient of performance, and whether they are good as those guys or not. Because those were made, like we created this. We created this because this curve is really nice. It requires a nice curve for you to do the job, right? So that curve is different for refrigerant than for water vapor, for example. One of them is more friendly for refrigeration cycle. Think about what's the ideal shape that you want, right? You want this guy to go like this, so that you immediately go up and you are ready to go in. So my graduate students actually have a paper that we are submitting it right now about how the different shapes of those curves can make, he's suggesting a new improvement to the cycle, refrigeration cycle. And he see that, sorry, he see that modification behave differently for different working fluid. So when you're working, but it work better for natural refrigerant. So that's what we are excited about. That for natural refrigerant, you can make the cycle better if you use new modification that he's proposed. Okay, so he is explaining to us what I just told you right now, right? So there's atmosphere, the chlorine had horrible effect, and there was international agreement that basically banned them. And now our problem is just like the high global warming potential and natural refrigerants. They are toxic, right? Flammable, right? Ammonia we can kill someone with ammonia, right? But ammonia has been used as a refrigerant in the past, like in the 60s and 40s, people were using a lot ammonia before they come up with those miracle molecules, right? All right. So now in this section, this is the beauty of reversing the condenser with the evaporator. So the outside unit, the inside unit, and they are connected by a compressor and expansion valve. Okay, but it doesn't have, so is that winter or summer? Can anyone tell me? Winter or summer? The exit of the compressor is going inside the house. Winter or summer? Winter. You're using the hot to be cooled inside your house. Okay? And then the cold here, you go outside to be heated. Right? So why is he's heated? Because he's even colder than the cold outside winter with. So winter is outside is like 20 or like 30. You are sending that refrigerant at 15. So you can get heated. So one time I had a problem like this in the final. And one student, after the exam was over, the student emailed and said, how is it possible that, and that was here, I was not heating the house. I was telling them this is a water heater working on a water pump, also working on a heat pump, and calculate, if the temperature outside is this much and temperature of the water inside, I want to heat the water at 100 degrees C or something, what is the COP? And that student said, well, how could the temperature outside be 20 and the water will not freeze? And that just stopped them from answering the question. I mean, they didn't get it. And after the exam was like a week or two or something, they emailed like, I just need to know, how does this work? What's the secret? How could a water heat pump work when the temperature outside is 20 degrees? The student's concern was, wouldn't the water freeze? You don't have water here. What is going on here? Some kind of refrigerant, R134, something that when you take him to 15 degrees outside, he's still a liquid. And actually he's ready to boil at 15 degrees. Okay, he's ready to boil there and he becomes saturated vapor at 15 degrees and the compressor will take him up all the way to 120 or something. And that's when he will heat your water all the way up to 100 because he's even hotter than the water. And then he will leave again. Okay. So he's saying that for the heat pump, it's gamma, okay, and the best gamma ever is what Carnot can give you, and that's TH over TH minus TC. And don't think that any cycle work on Carnot, because I see that all the time too. Students, like, you ask them about gamma of the cycle and you give him all the H's. He go for it's TH over TH minus TL. No, only if it's Carnot. Who said that that vapor compression cycle that you got from Lowe's is working Carnot? The chances are never. There is never gonna be a machine, real life machine that work on Carnot cycle. Right? We are just trying to get close. All right? And we don't really have to solve a problem, but same thing, he will say, let's read the vapor compression heat cycle with R134, working fluid. The building is maintained at 20 degrees C when the outside is 5 degrees C. Okay, the refrigerant flow rate is this much. Determine compressor power, and he give you H1, H2, and H3. Why he didn't give me H4? Huh? Same. It's 3 and 4 are the same. Throttling, right? So he wants the compressor power. That's easy, right? That's H2 minus H1. H2 minus H1 times M dot. Heat transfer provided to the building. How much is going to the building? It's H3 minus H2. 2 minus 3, right? 2 minus 3, because he get cooled inside. He get cooled inside the building. The building that's already hot at 20, winter kind of hot. That's 20, that's hot. By the way, what is the equation to turn from degree centigrade to degree Fahrenheit? You guys need to have this always in the head, in the back of your head. Do we know? If I have degree Fahrenheit and want to turn it to degree C, what do I do? Right, minus 32 multiplied by 5 over. The way that I tell myself that I shouldn't, like I don't forget, is that I say Fahrenheit is so high. Not only I subtract 32, and that's easy to remember because that's the freezing temperature, right? But I also multiply by 5 over 9. So I kill it, I try to kill it twice. I subtract 32 and then I hit it by 5 over 9. And if you just want to do it very quickly in your head, just take 30. Like what I do, I take 30 and then I divide by, multiply by half. That's usually easier to do it in your head. So 70 Fahrenheit, what's that? Take 30, that's 40, multiply by half, it's 20. Not really 20, it's probably going to be 20 something, right? But it's a good approximation, you know. Someone put the gun in your head and say, what is 17 degrees centigrade? 20. So the heat transfer provided to the building. So H minus H multiply M dot. H3 minus H2. And of course, the COP would be QH over work. Okay, pretty easy, right? If they give us the H's and ask for the work or the Q or the gamma, that is pretty easy problem. I think what be hard is when we have to get the H's ourselves. That is sometimes complicated. Yes, Robert.
So and the other thing with the extension valve, that's like
So the question for online people is, what is this throttling valve? How does it look like? So there is, if you look to all the fridges, that throttling valve was really a very tiny tube. A very tiny tube, huh? A very tiny tube that is basically coiled like this. Why it's so tiny? So that there's a huge pressure drop over it. So just by going through that tiny tube, the pressure has to drop. Friction losses, basically. And that's enough to drop the pressure and drop the temperature with it. But the throttling valve, what's really important in it is the control over it, right? So that how far you can throttle with it. So it will be something like this, and that will have the actuator will be pneumatic, something, or electric, where you can basically open the valve and close it. And usually there are two of them. There's two of them on the other side, on either side of before the evaporator and before the condenser, so that and it's bypassed by a check valve. So if the flow go into the stuff, the soft valve work and you drop the temperature. But if you come the other way, the check valve open the way and you bypass the throttling valve. I think. I don't know whether they have a good drawing for it or not. I think maybe in the book they have a good drawing. I think maybe not in the slide, but if you go to the actual textbook, you will find a good drawing of the throttling valve. But the point is, you are sending the flows through a very tiny hole or through a very long, tiny pipe so that the pressure just gets killed by going through it. So, you know, what I really wanted to show you is how they switch from winter to summer. And now it's done by that three-way valve. So that valve basically take the output of the compressor and either send it this way or send it that way. And it's a mechanical valve where it's basically just like you go right to left and the flow go here to here. And on both sides over here, you will see how there is like throttling valve and a check valve, depending on whether the flow is going this way or that way. Say that again. The heat exchanger in both sides are identical or not? Well, to start with, they have different geometry because the one outside is sitting in a square box like this, right? That's the one in the backyard. And so it has fans or have channels on 4 sides, right? And a big fan that sends the air, pull the air through it like this. But the one that's inside is usually connected to the air handling unit in your house. So it have a compressor that's blowing the air, and then there is that coil, cooling coil or heating coil. But it's a coil, but it's sitting here, and there's a filter before it so that you can get the dust before you get in. And sometimes people don't really clean that filter that much. But there's just like a filter over here and then the coil. So you can see there's not that much space inside. So usually inside smaller, but outside that big unit sitting on the outside, you really have a lot of space with a lot of surface area. So that really helps. But both of them, you can send either the hot or the cold refrigerant into it, right? So from that point of view, that work. All right. So now, what I would like to discuss is, especially in the context of that contest, and also to make you aware of what else can be done to this cycle. And there are some sketches really in the book that's really nice to look at too about this. But I want one of you, I don't want you to look at the book right now. I want you to try to invent this with me, okay? So we said that our problem with very high temperature difference is that the cycle COP will become really horrible if you have such a big delta T, okay? If this TH that you are trying to communicate with and this TL that you're trying to cool with, or like cool, If they have very big temperature difference, you can see why the COP will be small, right? The COP would be Q dot L over work. So what can we do to improve this? I am super sad about this, or like unsatisfied with such small Q dot L. My COP is almost going to be, you know, really, really tiny amount. Think about, look, see how much work I'm putting and how much Q dot L I'm. So what can we do in order to have heat pumps still work on a really big delta T? How can your boss told you this is miserable? What are we doing? I wish we can get big Q dot L, and you cannot change the refrigerant. That's the refrigerant we have to use. So that dome cannot change. You have to work with this particular shape. You know, you work with other fluid and it can get bigger, right? I mean, imagine if you have like something like this. I mean, wouldn't that be nice? But no, we are stuck with a blue guy. So what can you do to help this cycle? Say that again, move 3 to the left. Like go here. This require, unfortunately, what do you think this would require? What is that line? Temperature, that's the temperature. So I mean, this require, you are effectively reducing the temperature. No, you're stuck with TH. So you're stuck with this. This is as cold as you can get. Sorry. So what else? How can I make this Q dot L bigger? We want one of you to invent this cycle and be famous in the class. I mean, it was invented already, but you'll be famous in the class. You'll be known in this class as the one who invented the new cycle. We will give you credit for it. We will call it by your name for the rest of the semester. What should we do? I wish this can go a little bit to the right. Sorry, to the left. Anyway, we can take it to the left a little bit so that we can have considerable Q dot L. Okay, I'm going to invent this cycle and it's going to be called the Salam cycle from now on. Okay. Last chance to invent. Huh? Reheat? You are on the long pass, but right? Because remember in the power cycle, we went halfway and then we went up again. So what do you want to do? What do you want to do in this cycle here that's going like this and going like this? So like where do you want to do? Here's 1, 2, 3, 4. What do you want me to do? Huh? Between 3 and 4, do what? What do you want? You are in the right direction. What should I do in the middle here? What I'm trying to do? Your boss said, take it to me to the right, to the left. Give me some Q dot L, man. Okay, he said going to the right, to the left, so I'm going to take it to the left. Okay, I wish I was here. He would be happy. Okay, but if I am here, how can we get here? Huh? Yes, you are saying, what is that? Two cycles, huh? And this guy is being cooled by this guy. But this one will have good COP and this one will have good COP. Right? I have two condensers. And unfortunately here also, ouch. And also here I will have this condenser being cooled by this evaporator. Okay. Another way to do the same thing is, I don't wanna have two, but I could do what else? I could come here and in the middle, how can I do this? What's going on? How can I do that? You do a flash chamber. You lower the pressure. So this is 1, I guess now 2, and 3, and then 4, and then 5, and then 6, and then 7, and then 8, and then 9. So you come here at say 5, and you separate into 7 and 8. The liquid go down and the vapor go up to 8. And that 8 meets with, there's another compressor here that take you to 2, and 2 and 8 mixed together becomes 3. So that is the cooling in the middle, recooling or something. Just like the heating in the gas turbine, we would cool here a little bit. As a matter of fact, they do this cycle not just to increase this, but it's really for what is the benefit of this? What did I say about the compressor? It would be nice if the compressor get intercooling in the middle. So like why, like he's really at that point, no, the ambient is not going to help. The ambient is sitting over here. No one will cool us except us. We are cold already. We can take some of this vapor and cool the compressor with. And now, amazingly, this and plus this is way smaller than this. Have we went all the way in one stage compressor? That would be more work. But doing it in the first compressor, cooling, and then go second compressor will cool down. Make sense? Sound like a good project for the second project of the course to figure out, like, you know, like how much ratio do we need? I mean, I bet there is a compromise here between let's send everything to cooling and let's send everything down there. We'll find out, right? We could find out. But what I'm trying to excite you about is that there is this simple cycle, you know, people get famous by very simple modification. You know, like if we just ask ourselves, compressor sucks, man. It takes a lot of power. And we know from industry all the time, intercooler work, but it's so cold. What will cool him? We have refrigerant in our hand. Why don't we give him some? And then you become famous, and you become famous, and you have a new compressor that basically have intercooler in it. Right? So this is a well-established, like you can see, you know, refrigeration cycle that people brag about, like our model use this. Okay. All right, 5 minutes break, 5 minutes restroom break, and we will go through the homework and we'll discuss the last week homework just to make sure you got everything, and we will go through the project, and then we'll have a quiz at the end. All right. So let's go with the homework first because it's important also for the midterm. We don't have midterm next week, right? We have the midterm in what, maybe 2 weeks. When are we doing? When are we gonna have our midterm? October? Okay. Yeah, let's check. Yes, the midterm is way there, October 4th, right? We have time. But then you guys will forget too, so that's why we're not trying to remember. So this sketch is intimidating. I give you this, right? So many things. What it says here, what is W? Pound per hour. What's H? BTU per pound mass. F is Fahrenheit. A is the pressure in PSI absolute. What is PSI absolute and PSI gauge? Are you above the atmosphere? Then you are PSI gauge, right? What is 1 atmosphere? How much? Yeah, but how much in PSI? 14.7, right? So when it's like 2 atmosphere, the PSI gauge would be 29.4. That's 2 atmosphere. And the PSI absolute would be exactly adding the 2 of them together. So this is absolute pressure. And that's the one that we use in the steam table. I mean, we don't use the gauge pressure, right? So that's why it's nice. They give us everything else in PSI absolute, right? So when you look here, that is a 204A, meaning 204 PSI absolute. 113A, that's 113 PSI absolute, right? What are all those lines? Those are the bleeding line for the steam. So the steam come here at this pressure, 9.37, and he go at that flow rate. Actually, the mass flow rate were written all over this problem. Like this chart, the mass flow rate was all written. I just deleted them and wrote with my handwriting M.1 and M.2 and M.3, so then I can give it as a problem for the students. But when we got this chart from Jenks power plant, they actually they gave me like 4 charts for different loads. So you can see the chart at 100% load, and when they want to use the power, 75% and 50% and 25%. So I have that 4 chart at different power production. So this is at full load basically, right? And you can see they are doing at full load, what do you generate? You generate the rated power, the 480 megawatt. That's what you generate, but you dial it down and you get less and less and less, right? You get 75%, 50%, 25%. So this is the pressure it takes to go to full load, right? So many question was, where is the boiler? Where is the boiler? And obviously, whoever asked this was not in the classroom, because I said, you go, this is the boiler to the right. You send the flow to the boiler, you come back here. That's where you are coming back from the boiler. The boiler is the right corner of the screen. Okay? So you leave at 3 million and you come back at 3 million. And then where do you go? This is the steam chest. He sends you to the high pressure turbo. And then you leave going to the reheat. But before you send everything, you take some and you take them to M.7. What's that? That's the last feed water heater before the boiler. But the rest, which is now 2 million, 2.8, go to reheat and come back. So we go to the boiler twice. We go water here and you come back as steam. And then you come back again, you go back again as steam, but not that hot, so that you can get reheat and come back very hot. Right? 1,000, look at the temperature. I don't know why every time I try to make it bigger. See, ouch. You come back again at 1,000. So the first time you came from the boiler, you came at 1,000, and the second time you came also at 1,000. Right? So on the TS diagram, this cycle, TS for power cycle, BH for refrigeration cycle, right? So you came here at 1,000, expand a little bit, and then you go again when you come to 1,000, then you expand it. Right? So this is the reheat pressure that they are doing it. Yes. Right? So the water that went to the boiler to get to that hot was something like this. And this, just before you go to the boiler, this was the state where it left the heater 7. We call it HTR 17 for whatever reason. That heater 7, if I call this state, I don't know if we want to call this, what do you guys want to call it? So this is 1, 2, 3, 4, and let's call this 35 or something. So this is 35. And before that 35, the water here was 34. And how did the water go from 34 to 35? How did the water get that hot inside this heater? It's because of what? The steam that's coming at M.7, he basically heat the water, right? And he's coming from, where is he coming from? He's coming from this, from this. He's coming from state 2, the one that's going to the reheat. He's really hot, and he can do the job, and he can condense. And while he's condensing and doing this, going from 2 to, I don't know, let's call it 36. Going from 2 to 36, he can take the water from 34 to 35. Right? And what is this H2? And what is this H36? And what is this H35 and what this H34? Where do I get all those H's? The drawing, yes. The drawing tells us the H's of those 4 cases. Right? So if I come over here and read this chart, I'll be able to see that he's coming at 1266 H and he's leaving as 428. He's come as superheated and he leave as saturated liquid. Okay, not just saturated liquid, actually, he is a little bit cold. But anyway, I'm gonna explain why cold in a minute. But here is the H. So here is HN, H out. And the water, HN 420, H out 486. And I know the M dot. I know the M dot and I know the delta H. Do I know the Q that the water is absorbing from the steam? Do I know that or not? I do. It's what? How much? M dot water, the 3 million multiplied by H minus H, right? The 486 minus the 420. That's how much the water absorbed. Where did this come from? from m dot 7, h minus h. What's the unknown in this equation? Q equal Q. What's the unknown? M dot 7. And so I solve it by basically saying m dot water delta H equal m dot 7 delta H. Q equal Q. I get the H's from the chart. M dot water is given. The only thing that's ungiven is m dot 7. I get m dot 7. This is how much pound per hour. Question.
So I actually kind of got that. I thought it was going to be H outline. So how come it's supposed to be 6? I got a negative. I was just like,
So the question for people online is, if we stick to the sign convention you told us in the first law, and it's out minus n, and as a result, we got our m dot as negative. So what did this first law say? Yes, Q minus W equal m dot H out minus HN. So in that scenario, for the water, it would be 35 minus 34, right? That, putting the 3,200,000, whatever, 3 million, you know, work is 0, you will get Q here that is plus or negative? Plus, positive. Does this make sense? Yes, the water is being heated. First law say if you add Q, that is plus. That one, it's positive. Now, when we do it for the steam, what are you going to write for the steam? First law of thermodynamics for the steam side would say Q dot minus W dot equal to M dot. This is Q dot steam now. This was Q dot water. M dot steam, which is M dot 7, which what we are after, right? M dot 7, and then I'm going to say it's H, we call this 2. H2 minus H, no, we said out. First law say out. So 36 minus 2. This would be plus or minus? Minus, because 2 is way bigger than 36. Does it make sense that Q dot steam is negative? Yes, he's losing heat. First law is okay, right? But I wanted to say this equal to this, so I can get my m dot 7. Sure, go for it, but use the magnitude then. I mean, this is the same if we have a turbine running a compressor. Okay, and someone asks you to calculate for this m dot, find for me how much m dot compressor is. You apply the first law of thermodynamics here, and that power would be positive. You calculate the power of the compressor, and you apply the first law of thermodynamics and say Q dot minus W dot equal m dot, and it will be out minus n. Guess what is the compressor power would be? It would be negative. Does it make sense? Yes. If you are doing work on the compressor, it has to be negative. If you are doing work by the turbine, it has to be positive. But I want to equate the work to the work so I can get the m dot compressor. I want to say that work compressor equal to work turbine. Really? You're going to say work compressor equal work turbine? Are you going to say that the 300 kilowatt equal to the minus 300 kilowatt? No, you can't. You have to do this. You have to say the magnitude of the compressor equal to the final balancing my budget. Do I say my salary equal to my spending? No, my salary, let's say $1,000 per month equal to the magnitude of my spending, which is minus 1,000. Right? So if we gonna, I personally, I always love to just use the first law of thermodynamics, and I really enjoyed when I say W minus W work compressor, M dot, and you know, so that then when I get it negative, I'm happy. Makes sense? I'm okay. But then when you are trying to equate it with someone else, or trying to get work net, we talked about this when we talked about the pump. If you want to try to come up with work net in a in a Rankine cycle, turbine and pump, you cannot say it's work turbine minus work pump, and you put this guy minus 50, for example, kilowatt. If you want to stick to the first law, then it's work turbine plus work pump. And so it will be the 300 minus the 50. Right? If you don't want to, this sound weird and what you mean, then you do this minus work pump magnitude. Now it makes sense. You know, work pump is negative 50. Yes, it's a pump, take power. But when I try to calculate work net, I say work turbine minus the magnitude of work pump. Okay. So in that problem, you know, if you want to say Q steam equal to Q water, you better make the magnitude because you understand this is heating this. Okay, so George has a question. George, what's your question?
When putting the diagram together and determining the H's, after moving from the boiler through to the high pressure turbine, it kind of became muddy for me of how to decide the numbering for the H's. Is there a convention that is used?
So the question is, after like here coming from the boiler, that's fine. But then once you come in this network of pipes, like we get lost and we don't really know what's going on. Well, yes, it is complicated, but all we wanted was this heater. And all we wanted was that the H is just coming in and leaving. So I think this part is clear, right?
Yeah, that was understood which H's to use, but the numbering convention. Like like when you call it 34 and 35, after you get past
like
that
what should we label them?
Yes.
I mean, you can label them anything. I mean, if you start coding them from the start to the end, you can just put your number, but we don't really need to do all this, right?
Okay.
Because we are just solving for this guy. And it doesn't matter whether I'm going to call this 35 or 5. I can call this A, B, and C, and D, for example. I don't care.
Okay,
right?
perfect. So there's no convention for it, then that's good.
No, but however, for example, if I ask for this M dot, like now let's imagine the homework problem or the midterm, I ask for M dot 6. I tell you, I'm not gonna even say M dot 6, I just say how much steam is needed for the second or the one before the last feed water heater, or how much steam is needed for the last feed water feed water heater 6, right? What is going on? This guy, he call it heater 16. How much steam is coming here? Then you need to put a label here, M.6, and you would call this like M.7 or like 1 and 2 because you're going to use it. You have to call them in order. So let's try to do this together. How can I get M.6? In the midterm, he said calculate M.6 or M.3. Let's start with M.6. How do I calculate the steam needed to do this? What do I do? So you're saying multiply M.6 times this H, 1400, that's called 1400, and leaving that. So you are saying M dot H minus H equal to time this. So solve it exactly like the first problem. But did you see this? Did you see M.7? So what's going on here? The drain from M.7, yeah, the drain from M.7 is still hot. He doesn't want to throw it away. He want to use it. So the heating that happened here is not just M.6 time his, 1400 He's thinking, well, M.7 has 428. Then why don't I use it? So the heating comes from two places. So this is interesting. So to start with, on a TS diagram, this would be, here is the water, okay? And we call this like 36, 35, 34. This is the water in its way to the boiler. And it's being heated in the first feed water heater. And then it's being heated in the second feed water heater. It's coming at 34, then heated a little bit to 35, and heat a little bit to 36. And all the H's for the water is given to us. Okay? And we just solved for M.7. And now he's saying, give me M.6 too. I want to know this much. Okay? So we said that this is coming from here. So this is like state 2. And it does its job all the way and say, let's come here at I don't know, 37. It leave here at 37. Well, he realized that 37 is really hot, and he needs to do another job here. So this was coming at 2, and let's come this at 3. 3 was here. And 3 was heating the water from 34 to 36, right? While it is going down to 38. He's pulling M.7 from here, and he's pulling M.6 here. And again, to George's question, it makes sense to call this M.7 and this M.6 and this is M.5 and M.4 and M.3, right? So my number, like, or at least if I call them randomly M.13 and 14, I will just like get lost. But 7, 6, 5, higher temperature to lower temperature to lower temperature, that makes sense. So anyway, so see how this guy is actually hotter than 3, not joule wise, but temperature wise. He's really hot. So what they do is they dump it here, and by dumping it here, it's at higher pressure. So what they do is they throttle it. Same throttling that we did in the vapor compression cycle. They take that 37 and they throttle it to this. Let's call this 39, for example. What is the relation between H37 and H39? What is the relation between this H before throttling and the H after throttling? It's the same. Why? Why throttling is constant H? Because throttling is constant H. Because throttling is adiabatic and no work. Say that again. This is the TS diagram. Right. So throttling is not as entropic. There is loss of availability. You took this high pressure and you dump it down by a throttling valve or like a small pipe. Why? Because the pressure here is low. So it go down. Right? But the point now is, if I want to apply the first law to this new heater, not new heater, that heater, I will say energy in equal energy out. So the first law can be written very easily now by saying M.6 H3 plus M.7, right? M.7 H, go away. M.7 multiplied by H37 plus M.water multiplied by H34 equal, those are the 3 inputs. 3 inputs, steam from the top, water cascaded back from the first feed water heater, right? And the water, the main water line. Those are the input. What's the output? The new water, the hot water, M.water multiplied by H35 plus what's leaving from here? Yes, m.7 plus m.6. Those guys plus m.7 plus m.6, all those multiply by h38. So there is nothing complicated about this. This is nothing but m dot h equal m dot h, right? This is simply m dot sigma m dot h in equal sigma m dot h out, right? And in this equation, what is the unknown in this equation? Only one unknown, which is m.6. I just put m.6 on one side, put everything else on the other side, and solve for m.6. Okay? So, and yes, it was not required from you, but like in previous year, I would ask them to calculate this. And you can see here is the equation for the second feed water heater. Okay? And yes, it's not written in the way of sigma m dot nhn, but I can do this, but I don't want you to do this. This is, you can make a mistake by doing this. So I wrote it such that I know what's being heated by whom. So m dot water is being heated this much by m.6 going this way and m.7 going this way. This is another way to write it. It's not the most straightforward. The most straightforward is energy in equal energy out. Right? And you can get m.6. And the same thing happened at 5. So by the way, see how 6 and 7 and actually 1, 2, and 3 and 4, all those are closed feed water heater. What is a closed feed water heater? The water is going in the pipe, steam, and whatever is cascaded backward is dumped on the pipe, condensed on the pipe, but they don't mix. That's why m dot water coming in is the same as m dot water coming out. Okay? Pipes for the water, steam in the casing. This is different from this guy. What is this guy? It's called the aerator. Every power plant has to have a deaerator. What is a deaerator? A big tank. Okay, a big tank where what happened? The steam. Okay, I'm not gonna make it bigger. I'm sorry. Please don't go. Okay, a big tank where the steam is added to the water. They actually make it in a splash way. They let the water and the steam go against each other. They splash the water up, hit the steam with it, so that they can make a big mess in this tank, so that what happened? Undissolved gases like oxygen that got into the water from the condenser, because the condenser is under vacuum. So any small leak, the air will come in. In the deaerator, when the pressure is just right, they flash the steam with the water so that the air will leave. Okay, so those deaerator, if you look at their picture, you'll find out that it's really done so that you can see that part, so that you can release the air. Yes, it's heating, but it's really for this. It's really so that the air can leave from the outside. One big tank, this is the place where the water and the air come together. Sorry, the water and the steam mix together. Okay, see how it look like? Big tank with this water sprayed in the steam. Okay, you just want to make a big mess so that you can release the oxygen. And the pressure in here is such that it's above atmosphere. So when I open the vent, the air don't go into the water like what happened in the condenser. No, when I open the vent, it leaves. And you see always, any power plant has like a place where like things are leaving, the steam is venting. Right? So when it comes to the when it comes to the energy balance over here, what's the best way? Energy in 3n m dot 5 times its h plus this m dot times its h plus m dot 6 plus m dot 7 times its h equal to m dot water. So when I give them this one time in the exam, everyone almost got stuck in not knowing what is the m dot here. They know what's leaving is the 3 million. They know that what's coming here is 6 and 7, that they solved 4. M dot 5 is what we are trying. This problem is like calculate M dot 5 for me. So they got stuck at this M dot. They didn't know how much is coming into the feed water heater. How much you think is coming? No, try again. What is coming into the feed water heater? Into the deaerator, right? But it's a kind of feed water heater. It's open feed water heater. So how much flow rate is coming in? If 3 million is leaving or m dot water is leaving, how much is coming? Minus. Excellent. Why? Equation mass balance. You are telling yourself, I have to leave as m dot water. And you, in this place, you are dumping m dot 5 and 6 and 7 in me. And you are leaving with m dot water. Guess what's coming then? M dot water minus m dot 5 minus m dot 6 minus m dot 7. Right? And that is the mass flow rate throughout the pipe. You see that? So now throughout this pipe, from this point in, it's always m dot water minus m dot 5 minus m dot 6 minus m dot 7. So those 5 and 6 and 7 get added over here, and you come m dot water. And all those m dot, they're always cascaded backward until the last one get dumped over here in the condenser. So on a TS diagram, if I plot this, you will just see that every feed water heater is dumping on the lower one, right? They always reach here and come like this. Except the open one. The open one, that's 5. He gets 6 plus 7 from here, m dot plus m dot, and his own m dot 5. And then he leaves with m dot water that get the big pump that take him all the way up. Okay, so that pump, but everyone else is just go to saturation and then cascade back. Go saturation, cascade back. Until the last one that eventually go to the condenser, right? And they go here to the condenser. And that condenser take you to a big pump. It take you to a pump that basically do this for you until you go to the other pump. I know the sketch is horrible, so, but basically what I'm saying is there is this pump and there is this pump, right? And then there's another pump here also to take you higher. But if with one pump, all those at the same pressure, all those at the same pressure until you hit the feed water heater. Right? So if I want to draw this, the condenser come and here is his pump, and then you keep going all the way until you hit the open feed water heat. Okay, and so the water is like getting hotter until it goes this one. And then another pump that take you to this guy, and another pump that take you to, this was a supercritical, right? So there is this one pump that takes you supercritical. And then you expand in the turn. So big pump, they call this one, the one that takes you all the way up, that is the feed water pump. And it takes a lot of power compared to this and compared to this. Those are jokes compared to this one. This one is so big. This is the one that really gives you the pressure to the extent that This big pump, the feed water pump, it has its own what? It has its own turbine. So when you go to the power plant and you see the big high pressure turbine and the intermediate pressure turbine and the low pressure turbine, you see a smaller one on different shaft next to them is the BFPT, the boiler feed pump turbine. So a turbine coupled with the pump, because they realize that I cannot make electricity and then use the electricity to turn electric motor to turn a pump. I mean, if it's just a pump, I need a shaft. I have steam. I can make my own work, but from the turbine to the pump, and I cut the middleman. What's the middleman? The generator and the electric motor, that they have efficiency. And when it comes to that pump that do the main work, you know, I cannot afford to lose over generator and over. But the smaller one, those can run with electric current. That's okay, especially that they are far away too, right? They are not as close. This one is close to the turbine because they are close to the boiler. I mean, it's just like sitting there. So the logistic is that it's really close. We can just hook it up to the turbine on the same shaft. Okay. So what do I need you to learn from this? Just applying the first law of thermodynamics to a feed water heater, whether it's open and closed. How does the first law look like? Q equal Q. M dot delta H equal M dot delta H. Or sigma M dot H equal sigma M dot H. That's another way to see it. When there is multiple inlets, you know, an outlet, maybe it's easier to just say all coming equal all leaving. That's just like straightforward. But when there is only one guy heating one guy, steam heating water, all you have to do is M dot delta H of the water equal M dot delta H of the steam. And don't worry about the minus sign. Make sure that this is plus and this is plus. The heating guy equal to the guy that's being heated. Questions? Okay. So now the second part, how much was reheat? How much was the steam generator is actually using? Well, M dot times delta H plus M dot reheat times delta H. That's how they are sucking from us, right? And so you put those number here, the 3 million times delta H plus the 2 million times the delta H, you get this much. Now, the part that is always confusing every year is how I can get the heat rate. And I said, I want you to figure out what is the heat rate. And turn out the heat rate is the inverse of the efficiency, just with weird units. So the inverse of the efficiency would be still dimensions. If you tell me, give me 1 over eta, okay, it's Q added over work net. Isn't that 1 over eta? And the unit dimensions, but they wanted it to be in BTU per kilowatt hour. So the Q over the work in BTU per kilowatt hour. How do I do this? I know the Q. I just calculated the Q up there, right? And it's in BTU per hour. Why? Because the H's were all in BTU per pound mass, and the flow rate were in pound mass per hour. So pound mass per hour multiplied by BTU per hour become pound mass per hour multiplied by BTU per pound mass become BTU per hour. So the Q is ready for us. The question is the work net. And if I want to calculate the work net for something like this, then I mean something like this where you have continuous extraction, right? I mean you are extracting for all those M dots, right? And there is some reheat over here too. And there is like all those M dots and an even bunch of leakage, like there are like a lot of extraction lines from the turbine. So in every part of this, it's not the same M dot. So the way to do this is say work turbine is M dot water time delta H plus M dot reheat, the one coming from the heater time delta H plus M dot reheat minus M dot, 3 times the delta H plus M dot reheat minus M dot 3 minus M dot 4 time delta H. And by delta H, I mean delta H from here to here. Just this part on the turbine. That means that I need to go in this drawing and just like keep tracking what is the H here, 1300, and then what is the H here, 1321. So from here to here I have only this much, and then from here to here I have this much. It becomes it's a nightmare. Specifically also that you need to calculate this pump, and you don't really know what is this pump work. I mean, you know the delta H is done on it, but the pump work has efficiency associated with it. So the fact that the pump take you from this H to this H doesn't mean that the pump actually used this delta H. It used more. If the pump is giving you 100 kilowatt, does this mean that the pump consumed 100 kilowatt? It probably consumed more. So to calculate this and calculate this and calculate this power and subtract them from this nightmare over here so that I can come up with work net, that is not gonna work. But he still wants the work net of the power plant. What should I do? Huh? It's already given in the problem. That's why I always say that whenever he gets stuck, usually he didn't read the problem really well. It said a 481 megawatt power, like a steam power plant. That is the network, right? And that's also including the electric generator in it. And when it comes to the heat rate of the power plant, you really need to include the electric generator efficiency too. So that is the number we need to use. So that's 480 megawatt. So if I run for 1 hour, 481 megawatt power plant, how much megawatt hour will I get? 481 megawatt hour. If I have 100 kilowatt generator running for 1 hour, how much kilowatt hour will I get? Exactly the same number times 1 hour energy, right? So that's exactly what it consumes. So this over this, okay? And you get it in BTU per hour divided by kilowatt hour. It's really BTU per kilowatt hour. Make sense? Very good. I wish we have more time for discuss the projects, but I guess it's time for your quiz. So on a piece of paper, for 80% of the quiz, write whether you are at home or if you are in the class, you would write what is your class number. Sorry, what is your seat number in front of you. And then for the rest of the 20%, you're gonna solve this simple problem over here, which basically say you have a refrigerator that has this much QH and this much QL, and you want you to calculate the COP and plot it on the BH. How does it look in the BH? Straight line, isentropic, go down, right? So a plot and calculating the COP of a refrigerator. Don't forget to write what's given and what's required. So you write what's given and what's required, that's 40%, 30%. You write the equation, another 40%, final answer correct, you get 30%. All those, the quizzes itself is 20%. The attendance by itself is 80%. So everyone will always get an A, right? And when you are done, don't email it to me, upload it to the Dropbox. So the question, will you upload the homework solution to Canvas? No, I want you to just write it after me. So what did we say? We said the Q equal Q, M dot delta H equal M dot delta H. And we wrote that the Q reheat was M dot delta H plus M dot delta H. And finally, we said that the heat rate is Q added over work net. You see, this is the actual pH diagram of 134. You can see the kind of temperature that he has. If you're done and you took your picture and uploaded, we are done.
You did say that Q low was 7.81, right?
Yes, the heat removed from the refrigerated space, that is Q low. Right, so heat rejection to the environment, that's QH, and heat removal from the refrigerated space, that is by definition Q low. And why QH is bigger than Q low?
Probably because we're trying to remove heat from.
No, because the difference between them is. What's the difference between QH and QL? Why one of them is 8.99 and the other one is 7.81? What's between them? Work. Work is between them. Right? You add work to QL and you get QH.
Dr. Salam, will you be holding normal office hours this week?
Yes, just arrange with me. Just let me know when you want to see me and then or like Zoom with me and we can do it.
Okay, thank you, sir.
Okay. Okay, guys, you have to write that is QL and not QH because I'm going to turn off my monitor now. So write QH is 8.99, QL is 7.81, and required is the COP. Okay.